everyone, I'm Pragya Srivastava. I'm here to record a lecture on control system. The course code is KEC 602 and presently in my today's lecture we are going to start its unit 4, that is stability of linear control systems. Previously in my lecture we have studied various type of control systems and how the functioning of control system is governed and what is the behavior of control system with respect to various inputs. Let's say we have given step input, ramp input, parabolic input, impulse input, and we've also studied the time response. Now moving ahead in this course, we are going to study and analyze the stability. When a control system can be called stable, when a control system, the same control system can be called unstable, and when the same control system will be considered as marginally stable. So marginally stable is a new word coming up here. So marginally stable is a state where the system is at verge of getting unstable. Marginally stable is of course a class of stable system, but we are going to then again study that presently the system which is stable can enter into an unstable state, that is called marginally stable system. So moving ahead in this particular lecture, we will be studying the concept of stability. So why we need to investigate this stability, and then we will be studying some examples of unstable system, and of course then we have certain criteria using which we can predict the stability, that is Routh-Hurwitz stability criteria. So it is also called, I'm writing Routh-Hurwitz stability. So this is Routh-Hurwitz stability. Now for the same we will be studying some rules, some special cases, practical use, and then we have the references. Stability, the concept, the process to find out if the system is stable or not. Again, this word is a very vast word. A system is stable if every bounded input yields a bounded output. Now, bounded input means any input which has a boundary, any input which can be defined and is a deterministic signal, which perhaps which always will have boundaries and can be defined for a given limit. That is a bounded input. So let's say imagine a case when we are giving bounded input. If for those bounded input we have bounded output, that is predictable output, and unbounded output is like where there is no specific pattern, and this output is like moving ahead to infinite and some random signal, and this random behavior is going and you cannot measure it, so it is unbounded. So everything such like that is called as unbounded. A system is unstable if any bounded input, means you are giving a bounded input, still it gives and it yields a unbounded output. So you are giving a stable and bounded input and it is producing an unbounded output. So that particular system is called unstable. So a system which will yield a unbounded output for a bounded input, that is called an unstable system. So as simple as that, the condition of stability is quite clear now. Moving ahead, why we need to find out and predict stability. Investigate stability means we want to predict stability before realizing it, before realizing the system. So why is that needed? Why we need to predict stability before realizing a system in real time? So the most important issue to design a control system is the stability itself. An unstable feedback system is of no practical value. The stable system should exhibit a bounded output if the corresponding inputs were bounded. So the first is the foremost important point. Like most important issue to design a control system. Let's say we are going to design something. Let's say we are going to achieve some target, and when we are practically implementing that system, when we are practically implementing that control system in the real life, in the real time, then what is happening? Are we able to manage, and is that design successful in all the respects? Let's see a case and then find out what happens when we land up designing an unstable system. See, this is a very famous example of unstable system, the dramatic photographs showing the collapse of Tacoma Narrows Suspension Bridge in November 1940. So what is happening? The bridge was laid down with a huge amount of investment, and the photograph one is showing the twisting motion of the bridge center span just before the failure. You can see that this is a twist which can be seen in this bridge. A few minutes after the first piece of concrete fell, this second photograph shows a 600 feet section of the bridge breaking out of the suspension span and turning upside down as a crashed in Puget Sound in Washington. And you can see that the complete member of this bridge fell down. So this complete ridge is there between. So what is happening? This is a lack of planning. This is a failure of a system. Like, the system was not predicted to be performing in a stable environment. The system was not predicted as a perfectly standalone, withstand all the condition in the physical environment where the system was implemented. So here we can see that such failure can be very easily avoided if we can predict the stability of a system. What will happen to the system when the system is implemented in real time? So this is just an example of implementing the stability analysis and the stability prediction to a system. So we can study the different methods to realize and to predict the stability. Now next, this is nothing but we can say it is, we call it sigma plus j omega are the two vectors. Sigma lies on the real part, we also call it as sigma, and omega is the frequency which is lying with the imaginary part. So sigma plus j omega is a S-plane, defined as S-plane, where we will be implementing and trying to place all the poles of the system in this plane, in this sigma plus j omega metric. Now, what will happen and how can we predict the stability of a system? Just by looking into this S-plane. What helps us in this? Now, we can see that there is a gray and a shady region, which is also mentioned as, this gray and a shady region is written as unstable region. So this is very correctly written as unstable region. This complete region is an unstable region. Any roots, any value of S, S1 and S2, the roots of any equation having placed in this unstable region, in this part of the S-plane, like right hand RHS of the S-plane, the system will turn out and will result into unstable system. That is a fact. Now, we can predict, let's say a pole is lying here, a pole is again lying here, a 0 is lying here. Okay, we talk about poles only. So whenever we are on the left hand side or we are just on the margin, what is the margin? How can we define the margin here? So margin is this complete thing. So this is a zone of marginally stable system. This is marginally stable location of roots if the roots are lying on this imaginary part of g omega axis. We will call the system to be marginally stable. So again I'm defining, previously also I have defined what will be a marginally stable system. A marginally stable system will be called as a stable system only. It is a stable system. It is a class of stable system. It is a kind of stable system. It is a condition of stable system only, but it is at the verge of getting unstable. Okay, any parameter changing up and down, any slight change can lead the system to enter into unstable region. So that is all we can learn about this S-plane. So this was stability region according to the roots obtained by the characteristic equation. Now again, characteristic equation we know. Characteristic equation, let's say we have a transfer function here. Transfer function is let us take an example of negative feedback only. So it is 1 plus gs hs. So characteristic equation is nothing but what we are trying to do. We will just equate this portion to 0. So this becomes the characteristic equation. So characteristic equation is denominator of the transfer function equated to 0. So when the roots of this equation, of course this will be a polynomial in terms of s. So like let us take example of, let this be s square plus 4s plus 8. So let's now equate it to 0. And of course, you will find two values of s, s1 and s2. So these are the roots. So depending on the location of these roots, this complete system can be said stable or unstable. Next, using these concepts, we can say stable system if the natural response approaches 0 as time approaches infinity. Okay, that is a stable system. Like when we talk about infinity time approach, then the natural response and the natural tendency of the system should, the output of the system should reach 0 ideally. Now, what is the unstable system? If the natural response grows without bound as time approaches infinity. I have drawn a previous figure. Okay, like the natural response when there is no bound. Okay, and I am not able to predict what will happen next. So that is a class of unstable system. Now, marginally stable system. If a natural response either decays nor grows, but remain constant and oscillates as time approach infinity, like this. It is neither falling, it is nor extending. Just I'll go out of the board, but it will remain the way it is. So this is called a marginally stable system. And let me draw a stable system as well. So this is a stable system. Okay, so as the time is approaching infinity, the output is getting 0. So this is the first case, stable system. Second case, unstable system. And the third case, which is marginally stable system. And then from here we can have this is okay. I have drawn in the previous case and it is here pictorially representing here. Let us see the last case. Isn't this case 2 where the output is getting unbounded, and here it is getting unbounded. You are not able to predict it. Previously it was within the limits, now it is extending and extending. So this is unstable. So corresponding to unstable, you see, for an unstable system, the roots have to, for an unstable system, the roots have to lie on this portion. And we can see that the roots are lying. So this is a region of roots for system to become unstable. So we can see that the roots were lying in that region and corresponding response is unstable. So let's talk about all remaining cases, and one by one we will take where the system, one by one we'll take where the roots are real. Okay, so roots are real. So for real roots we can have a very easily predicted response. So it is going, we will have certain expression and we will have certain equations of CT, so that you can relate that how one root will result in that graph. But of course we can, for now we can make it very clear that the system is either stable or unstable. So it is very clearly, you can predict the path, and as the time approaches infinity, it is going straight only. So stable. Next is, we can see that it is positive real root. Again, we have to notice that it is coming in the region of negative half. Sorry, right hand side of the S plane. So right hand side of the S plane, we are telling this system to be unstable, and you know it is going like this. Now where it is going, I am not able to predict. So it is unstable. Unstable. This one is stable. Now here we have complex conjugate roots, but they are lying on the left hand side of the S plane. So left hand side of the S plane, you can see that the nature, it is not going unbounded. It is diminishing, and a time will come that it will approach some constant value. So very much predictable. So we can call it a stable system. Contributions of characteristic equation roots to closed loop response. So these are the different cases, and we'll be able to predict the stability in this way. Now, studying the most famous method to predict the stability of any characteristic equation. Of course, the characteristic equation will be a polynomial in terms of S, that is Routh-Hurwitz criteria. Okay, so in the Routh-Hurwitz criteria, we can see that first we have to examine the characteristic equation, and we have to see that whether the characteristic equation is eligible for Routh-Hurwitz criteria or not. So for those things, we will see certain eligibility criteria, like there shouldn't be any power of S missing in the polynomial. Let's see that criteria itself. Rules. There shouldn't be any missing term, no missing term, like S raised to the power 4, very good, S raised to the power 3, very good, S raised to the power 2, where is it? X into S raised to the power 2. This term is missing, because straight away from 3, you are coming on to S raised to the power 1, S raised to the power 0. So, of course, S raised to the power 2 is missing. So, we cannot use Routh-Hurwitz here. Okay. All variables should be of the same sign, like 5s cube minus 3s square plus 5s plus 1 equals to 0. So, negative sign before the variable 3. One more thing, none of the coefficients should be an exponential term, like this 3s, like this 3. We should not have any term e raised to the power minus 3t, or sorry, anything related to S domain. So then there shouldn't be any trigonometric coefficient, there should not be any exponential coefficient. So these are certain rules which we need to follow before going for Routh-Hurwitz criteria. Now, there are certain rules. Using these rules, we'll be able to solve Routh-Hurwitz criteria. So first we need to write and construct a Routh table. How we actually construct a Routh table. Now, let's say we are considering a polynomial. So I'm making a polynomial. Let's say 4s to the power 4 plus 3s to the power 3 plus 6s square, and then let's say we have 2s plus 1 equal to 0. So this is a polynomial. Then what we'll do? We will write, like, the highest power is s raised to the power 4. We'll write s raised to the power 4, then s raised to the power 3, then s raised to the power 2, then s raised to the power 1. That's it. Now again, here is s raised to the power 0. So these two columns will come from the equation itself. These two columns will come from the equation itself. So this is s raised to the power 4. This 4 is a even power of s. So all the coefficients of even power will come. So coefficients of even power, like s raised to the power 4 is even, s raised to the power 2 is even, s raised to the power 0 is even. So we have to consider, we will be writing 4, 6 and 1. That row is complete. Now we have to see s raised to the power 3. S raised to the power 3 is nothing but, we have to consider all the odd coefficients, 3, 2 and then we don't have any. So we are writing 3 and then 2. So this is a table, and then filling this complete terms we will be studying in my next lecture, how this Routh table and how this complete table can be framed, and then we can predict stability. So we will study and solve a complete numerical on Routh-Hurwitz stability criteria in my next lecture. Thank you.